What's up? It's Eli Kilgore, and this is my Physics 2211 Lab 3 on black hole. So, in part 1 of my lab, I used glow script coding in order to find the mass of the black hole, and we utilized Newton's second law to do this. The system of part 1 was the planet, and the source was the black hole. In part 2, we used mass to determine the velocity of the spaceship needed in order for it to escape the black hole. The system of part 2 was the ship, and the source was the planet and the moon. The main principles used in this lab in part 1 were that force is equal to change in momentum over changing time, and the gravitational force formula, which is shown. In part 2, we again used the momentum and gravitational force formulas, and then position update as well. So now I'm going to show you my part 1 and part 2 analysis on the glow script coding. So my code for part 1 starts right here. I found the initial velocity and final, and then used that to find the momentum initial and final. The change in velocity being the v final minus v initial, and then change in momentum being the same. And then I found the change in momentum over time, which is equal to net force. Using this, I found the parallel and perpendicular forces of net force, and then I use these to calculate the mass of the black hole. And the orbit can be shown here. As you can see, the planet is orbiting the black hole. The arrows are showing the perpendicular and net force vectors, and then at the end, my average value for the mass of the black hole is shown right here. Now on part 2, my code begins right here, where I found the force of the planet on the moon, the force of the ship on the moon, and then found the net force on the moon, and then the force of the planet on the ship, the force of the moon on the ship, and then using this, the net force on the ship. And I use this to update the moon's velocity and the moon's position, the ship's velocity, the ship's position in order for the graph to fully execute. So here is our graph. In the middle is the planet, the blue is the moon, and the purple is the ship, which has an uneven orbit because it was orbiting the moon and the planet. And now I will go back to my slideshow. So, what does this mean? The rate of change of momentum has a direct relationship with the rate of change of velocity because the mass is always a constant value and momentum is equal to mass times velocity. The net force is the total forces acting on the body, which will be shown as, let's say in the second lab, the total forces acting on the ship were the gravitational force from the moon and the gravitational force from the planet. So by these two formulas I just spoke about, we can infer that net force and change in momentum are different, but they're equal value. If we wanted to predict the motion of the entire system, we would have to find the values of the ship on the planet and the moon on the planet as well, because the ship and the moon create small gravitational forces upon the planet as well. Using this, we could find that the movement of the entire system is zero. It stays constant, but each individual component, being the ship, planet, and moon, all move at different magnitudes due to the forces of the other components on the system, and they will act in balance along this. So some possible sources of air in part 1, there could be other planets around that help pull the planet out of the orbit of the black hole, which means that finding the orbital or the escape velocity of the black hole for just the one planet would not be fully accurate because there's other forces upon it. And this is very similar in part 2. There could be air of other planets pulling the ship and the moon away, which would change their orbits or even pull them out of orbit, and we can't account for this since we don't know of the other planets in this. Also, since the speed in the second glow script code was found through trial, the speed could have possibly been guessed wrong, and that could change the orbit that was supposed to happen. Uh, Thank you guys for watching. That's all.